So we've been talking a little bit about how the derivative looks based on what a function looks like, or what some of the relationships between functions and their derivatives are. We're going to do a lot more of investigation with that today. Specifically with the equations of functions, we're going to figure out all kinds of stuff about them, when they're increasing, when they're decreasing, when they have local maxes and local mins, points of inflection, when concavity changes, all that kind of stuff. So we're going to start with the easiest part of this, which is when do functions increase and when do functions decrease? And this is something we've already talked about. We know that functions increase if their derivative is positive, and we know that functions decrease if their derivative is negative, right? So that's something we've already talked about before. And we want to make sure when we do intervals on which functions increase and decrease, that we always indicate it using brackets. I don't agree with this, but the College Board wants you to do it. So whenever we do increasing and decreasing, we're going to use brackets. Sound good so far? Yes, no, maybe. If the derivative is positive, the function increases. If the derivative is negative, the function decreases. So we're going to start with a function that we know a lot about already, the function f of x equals x squared. We should know when that is rising, or when it's increasing, when it's falling, or when it's decreasing already. But we're going to use what we call the first derivative test, which means we're going to take the derivative of it. And what's f prime of x?
2x.
2x. And then we're going to look at when that's positive and when that's negative. So in order to do that, we're going to find the critical values. So we're going to figure out when that's 0 and when that's undefined, because the only time that that could change from being positive to negative is if it's 0 or if it's undefined. So first off, when is this equal to 0?
X equals 0.
Okay, and when is it undefined?
Never.
Right, never undefined, right? And we'll see that a lot today, that it's never going to it's not always going to be undefined, but a lot of the time it's going to be always defined. And anytime your derivative is a polynomial, it's always going to be defined for all real numbers. So what we'll do is we'll say the only place that the derivative could possibly change from being positive to negative is at x equals 0. So we'll make a sign chart, okay? And we're going to put 0, the one value we found, in the middle of our sign chart, and we're going to investigate what the derivative does to the right of 0 and to the left of 0. So if we plug in a positive number, like 1,000, what does my derivative become? Our derivative is
positive.
Positive if we plug in a positive number, and which tells us the function is increasing. And if we plug in a negative number, our derivative is negative, which tells us that our function is decreasing. And so we would indicate that this function is decreasing on the interval from negative infinity to 0, and that it is increasing on the interval from 0 to infinity. And I know I said we'll always use brackets. We'll always use brackets on increasing and decreasing unless it's on infinity values. So if it's negative infinity and positive infinity, we'll still use a parenthesis. But for any other values, even if they're shared, they still want you to use a bracket, even though to me that doesn't make any sense. Because how could the function both be decreasing and increasing at 0? It can't. It's either one or the other, or it's neither. Can't be doing both. Good or no? Any questions on that? Any questions? You guys all good?
We're good.
All right. So now we want to figure out when this function x cubed minus 4x is increasing or decreasing. This is one we probably don't already know right off the bat. Right? We're going to have to actually do all the derivative stuff to figure it out. Could have just done the other one by knowing what that function looks like. So if we have x cubed minus 4x, we can take its derivative, and what's f prime equal?
3x squared minus 4.
All right, 3x squared minus 4. And first off, when is that undefined?
Never.
Right, never undefined. And when does it equal 0? When x equals what? Or we could say x squared equals 4/3, so x would equal positive or negative 2 over the square root of 3. So we'll make a sign chart and put those two values on. And then I'd like you guys to take a second to plug in the numbers and see what happens on your sign chart. So take a second, plug in those numbers, and let me know what you get. So hopefully you plugged in something between negative 2 over root 3 and 2 over root 3, like 0. 0 is usually an easy value to choose. So if you plug it in 0, did you get a positive or negative value for your derivative?
Negative.
Right, f of 0 was less than 0, which tells us our function is decreasing. Plug in something more than 2 over root 3, like 1,000, right? We'll say f of 1,000 is positive or negative. We plug that in.
Positive.
Positive. Okay? And so our function should be increasing. And plug in negative 1,000 or something else less than negative 2 over root 3. And what do you get? Square that, it's a very large positive, and it still is positive. Is that what you guys all got?
Yes.
Great. So we would then say that our function is increasing on the interval from negative infinity to negative 2 over root 3 with a bracket, union 2 over root 3 to infinity with a parenthesis, and decreasing from negative 2 over root 3 to 2 over root 3. Any questions or issues with that? All right, so what do you think is happening at x equals negative 2 over root 3 on our graph?
The derivative equals 0, so it just kind of like levels off.
Right, it levels off and it goes from increasing to decreasing. So that should be a local what?
Max.
Maximum. And at 2 over root 3, it should be a local minimum, right? Just like here, we know that at x equals 0 for x squared, we have a local minimum. Well, that's what our sign chart is also showing us, is that we have a local minimum there. And so that's the next thing we're going to talk about, is when we have local maxes and mins. So if our derivative changes from positive to negative, meaning our function goes from increasing to decreasing, then we should have a local maximum. And if our function goes from derivative goes from negative to positive, that's telling us that our function goes from decreasing to increasing, and we have a local minimum. Yeah. Now, it's possible that our derivative might not change signs at that value, in which case there is not a local max or a local min. And we can apply the same types of things at endpoints. So if we have a left endpoint and our derivative is positive to the right, then our function increases to the right and we have a local min, and so on. I think the endpoint ones are kind of self-explanatory. Good or no? So let's use the function x cubed minus 12x minus 5. And using the first derivative, we're going to find any local extreme values and determine if any of them are absolute extrema. So what's the first thing we'll need to do with this?
Find the derivative.
Right, so f prime should be what?
Three x squared minus 12.
Okay, 3x squared minus 12, good. And when is that undefined? Hopefully never. And when does that equal 0? We can take out the 3, it becomes 3 times x plus 2x minus 2. And so that'd be at x equals positive or negative 2. So we'll make a sign chart and plug in something between negative 2 and 2, like 0. And what do we get, a positive or a negative?
Negative.
Get a negative, so our function should be decreasing. Plug in something more than 2, like 1,000, and what do we get?
Positive.
Positive, so it's increasing. And plug in something less than negative 2, like negative 1,000, and what do we get?
Positive.
We get another positive. So we can see that our function is increasing from negative infinity to negative 2, decreasing from negative 2 to 2, and increasing again from 2 to infinity. And we're looking for local extrema. So that means we're going to have a local max at x equals negative 2 and a local min at x equals 2. Good or no?
Good.
All right, let's find those values. So what's f of negative 2? And what's f of 2? It's like f of negative 2 is 11, I think. And f of 2 is negative, what is that? Negative 21. You guys agree with those?
Yes.
Yeah. All right. So we would say that we have a local max of 11 at x equals negative 2 and a local min of negative 21 at x equals negative 2. Any issues with that? Everybody good?
Wait, isn't the local minimum at x equals 2?
Oh, yeah, sorry. I don't know why I wrote negative 2. I think I said negative 2 too. Sorry, at x equals 2. Everybody good there? All right. So now we're going to do this with a function we definitely don't know much about. X squared minus 3 times e to the x. So I want you guys to take a second to try and take your first derivative of this on your own. So take a minute and figure out that derivative. What did you guys get for your derivative there?
I used the product rule, so I got like e to the x times x squared minus 3 plus e to the x times 2x.
Yep, exactly. And to figure out when that equals 0, we're going to want to factor out the e to the x from it. So that gives us e to the x times x squared plus 2x minus 3, or e to the x times x plus 3 times x minus 1. Everybody good with that?
Yes.
All right. First off, when is this undefined?
It's never undefined.
Right, never undefined, because I can take e and raise it to any number as a power, and I can do this plus 3 or minus 1 to any number and multiply them together. So never undefined. And when does it equal 0? Well, when e to the x equals 0, or when x plus 3 equals 0, or when x minus 1 equals 0. So negative 3 and 1. And when does e to the x equal 0?
Never.
Never. So we've got two values to put onto our sign chart. What's something between negative 3 and 1?
0.
0, yeah. So plug in 0. This is e to the 0. In fact, e to any number is always going to be positive, right? We take a positive number and raise it to any power, we get a positive. So this is always positive. And then 0 plus 3 is positive, and 0 minus 1 is negative. So we end up with a negative in between there. What about something more than 1, like 1,000? Positive, positive, and positive. And negative 1,000 would be positive, negative, negative, or positive. Everybody good with that or no? Any questions on that? Good with that or no? All right, we'll assume that's a yes. Okay. So we know we have a local max at negative 3 and a local min at 1. And so let's try and figure out what those values are. What's f of negative 3 and what's f of 1? It's like f of 1 is negative 2 times e. And f of negative 3 would be 6 e to the negative 3, or 6 over e cubed. Everybody good there or no?
Should we actually like calculate, like approximate it, or do you just want us to leave it in terms of e?
No, in terms of e is fine. If you were graphing it or something, you need to approximate it just to know about what it is, but that's fine. So we have a local max of 6 over e cubed, and we have a local min of negative 2e, and this one is at negative 3, and this is at 1. And it asks us to identify if any of these are absolute extreme also, which it actually asked us to do on this last one, and I forgot to do it. So let's go back to the last one and determine if either 11 or negative 21 is an absolute extrema. So we know that we have a local max, but it's decreasing. And we know that we have a local min, but then it's increasing after. So how would we know if this function increases higher up than our local max of 11 or decreases down here to something less than negative 21? What would we have to find?
And behavior.
In behavior, right? Which we should know because this is a cubic. But in the behavior really is a limit as x approaches infinity. So as x approaches infinity of f of x, we end up with infinity, which means that 11 is not an absolute max. It's just a local max because as we go towards infinity, we increase without bound. right? It gets as large as it wants to be. And similarly, if we look at the limit as x approaches negative infinity of f of x, well, that becomes negative infinity cubed, which is negative infinity. And so it decreases without bound to a number far less than negative 21. So this tells us no absolute extrema. I forgot to do that there. Hopefully that makes sense. We're going to do it with this one and see if that's still the case. It looks like it, right? Because it looks like it's increasing and it looks like it's decreasing forever. But let's find those limits. So the limit as x approaches infinity of e to the x times x squared minus 3. That's what it was, right? X squared minus 3. So as x goes towards infinity, what does this become? E to the x is infinity, right? And x squared minus 3 is infinity. So I have an infinity times an infinity, which is just going to make it bigger. Infinity, right? What about the limit as x approaches negative infinity of e to the x times x squared minus 3? Effectively, what does that become? That becomes like x squared minus 3 over e to the infinity as x goes towards infinity, which becomes what? I could have written that as an infinity squared, right? Which one of those increases more rapidly, the numerator or the denominator?
Denominator.
And so therefore, what should this be approaching?
0.
0. So we have a horizontal asymptote to the left of y equals 0. And so that means that as this decreases, it does decrease forever, but it's decreasing to a horizontal asymptote. Is it going to go back below negative 2e? If it's approaching a horizontal asymptote of y equals 0?
No.
Nope. So our value at negative 2e is also absolute. But our value at negative 3 is not absolute because our function increases without bound as x goes towards infinity. And I'll throw this up on Desmos real quick just so we can take a look at it. Our function was e to the x, right, times x squared minus 3. And that's exactly what we've got. We've got a horizontal asymptote to the left of y equals 0. We hit this local max at x equals negative 3 of 6 over e cubed, which apparently is about 0.299. Cross through the x-axis. Hit a local minimum here at 1 comma negative 2e. There's our absolute max. Our absolute min. And then we increase without bound after that. Everybody see how that works out?
Yeah.
All right. So slowly, as we go through and learn all this fun calculus stuff, we're piecing all the different skills we need together to really get a good picture of what any graph looks like. So the next thing we need to be able to do with that then is figure out about concavity. So I think we talked a little bit about concavity the other day. Is that true?
Yeah.
Yeah. So when we talked about concavity the other day, I think we just mentioned like this is concave up and this is concave down. And did we talk about the second derivative at all or no?
No.
No.
Sorry, that a yeah or no?
We did
No.
not talk about second derivative.
We did not. Okay. So we're going to start then talking just about derivatives. If the derivative is increasing, the function is concave up. So the derivative, suppose this is my function that's concave up. The derivative is just the slopes of the tangent lines. Well, approximate, oh, that was horribly drawn. Approximate the slope of that tangent line for me. Pretend I drew it properly, like it's actually a tangent line. What's the slope of that?
-5.
-5, sure. What about this one? All right, -2, I'll do it. Approximately -2, yeah? Did we increase from -5 to -2? We did, right? The derivative increased from -5 to -2. What about here? What is it there?
0.
0. We increased from -2 to 0. Now it becomes positive. Oh, that was really bad. Positive, like 1 and then 6 or something. Right? Our derivatives are increasing because the function is concave up. Here we start with a value like 5, and then they decrease, right? They go from large positives to 0 to large negatives. So if the derivative is increasing, the function is concave up, and if the derivative is decreasing, the function is concave down. Well, if y prime is increasing, what does that tell you about its derivative? Y double prime must be positive. And if y prime is decreasing, that ought to tell you that y double prime is negative, just based on the first derivative test, right? If my function is y prime and it's increasing, then its derivative must be positive. And if that function is decreasing, its derivative must be negative. Does that make sense? So we can kind of piece this together and say that if y double prime is positive, we are concave up. So if our second derivative is positive, the function is concave up. And if the second derivative is negative, then we are concave down. Any questions on that? You all still alive out there?
Questionably.
Okay. Are we having any issues with this, or are we okay?
I think we're okay.
All right, and just a lot of silence, so I'm making sure. All right, we're going to go back to the simple function that we started with, x squared. We know what about x squared and its concavity already before we do anything.
Concave up.
We know that it's concave up, right? No matter what, for the entire domain, right? Y equals x squared, that's the definition of concave up, right? That's the concave up parabola, right? So if we were to take the derivatives, we should see that the second derivative is always positive. So we don't care about the first derivative other than that we need it to get to the second derivative. Our second derivative is 2. 2, no matter what x value I plug in to 2, right? 2 is still always positive, right? And if 2 is always positive, the second derivative is always positive, which tells us that this function is always concave up. And that should be something that we, like we said, already knew at the beginning, but we've now proved it using a little bit of calculus. Does that make sense? Everyone good there or no?
Makes sense.
Cool. All right. Let's take a look at this function, 2 plus sine x on the interval 0 to 2 pi. We want to determine the concavity on 0 to 2 pi of 2 plus sine x. So how are we going to do that?
Find the derivatives.
Yep. First derivative is what?
Cosine x.
Cosine x. And second derivative is?
Negative sine x.
Great. Okay, so negative sine x. And so we want to know, when is negative sine x equal to 0 and when is negative sine x undefined? So first off, it's never undefined, right? And when does that equal 0 on the interval from 0 to 2 pi?
0 and 2 pi.
So we got an open interval, so not 0 and not 2 pi because they're not actually included. So really just pi. Right. 0 and 2 pi are also places, but we can't include them as places where we might have changes in concavity because 0 and 2 pi are defined for this interval. Does that make sense? Now I'm going to put those values on here just so that I'm careful when I plug things onto my sign chart to make sure I don't plug something less than 0 or something more than 2 pi in. So we're plugging something between 0 and pi in, like pi over 2. What's negative sine of pi over 2? Is that positive or negative?
Negative.
Yeah, negative. So our function is concave down on that interval. And between pi and 2 pi, we end up with something that's positive, and it's concave up. Any questions or issues on that? So we can say concave down, 0 to pi. And in this case, we're allowed to use the parentheses because the College Board likes to contradict themselves. And we'll do pi to 2 pi in parentheses also. Everybody good with that?
Oh, wait. So for the parentheses, so you have parentheses when it's for concavity, but for increasing or decreasing, it's closed interval?
Yep, because the College Board is what they are. I disagree. I
Okay.
think they should all be parentheses, but you got to use the brackets because you got to take the AP test. So, yeah.
Okay, thank you.
No problem. All right, so let's take a look at one more here. We're going to try to find points of inflection, and so we should be familiar with points of inflection are, right? Points of inflection are places where the concavity of a function changes. Okay, so we're going to look for sign changes in our second derivative. So here we had a sign change at pi, which tells us that we would have had a point of inflection at pi. Okay, so we're going to do the same thing here for y equals e to the negative x squared. So first off, we'll need a first derivative. And what's the first derivative of e to the negative x squared? What's the derivative of e to the u? The derivative of e to the u is e to the u times the derivative of u. Yeah? Everybody good with that or no?
Yes.
Okay. Now we need our second derivative. The second derivative is going to require us to use the product rule because now it's negative 2x, one function, times e to the negative x squared, another function. So that's going to give us what? Negative 2x times the derivative of e to the negative x squared, which we already found to be negative 2x times e to the negative x squared, plus e to the negative x squared times the derivative of negative 2x. And what can we factor out of that?
E to the negative x squared.
Exactly. So we'll take out the e to the negative x squared, and what are we left with? We're left with 4x squared and a minus 2. And so first off, when is that undefined?
Never.
Never undefined still, right? Because I can do 4x squared minus 2 to any number, and I can square any number, and I can make that thing negative, and I can raise it as a power of e for anything. So never undefined. So then we'll see when it's equal to 0. Is e to the negative x squared ever going to equal 0?
No.
Nope. So all we have to do is this 4x squared minus 2 part equal to 0, which gives us x equals plus or minus what? The square root of a half, or plus or minus 1 over root 2. Good or no?
Yeah.
All right, spectacular. So let's make our sign chart. Negative 1 over root 2 and 1 over root 2. Plug in a value in between, like 0. And what is your second derivative? What is the sign of your second derivative if you plug in 0? E to any power is always positive, and this is negative, so it's concave down in there. And then something greater than 1 over root 2 would be like 1,000. This is, like I said, always positive. And then this becomes positive. And then something like negative 1,000, still positive, and positive concave up. So how many points of inflection do we have?
2.
Yeah, 2 points of inflection. One at negative 1 over root 2 and the other at 1 over root 2. We'll find the values of our function there. So what are the values of our function? Y of 1 over root 2 and y of negative 1 over root 2 should come out to be what? 1 over root 2 squared is a half. And e to the negative 1/2 is 1 over root e. Same here. If I square the negative 1 over root 2, we get a half, get the negative 1/2, and we get e to the negative 1/2 or 1 over root e. Everybody good with that? Any questions there?
Wait, so with the sign chart, do you automatically know that 2 consecutive segments are going to be of different signs, or do you have to plug it in every time?
You have to plug it in because they won't necessarily always be. Actually, that's what the next thing I'm going to talk about. But yeah, you got to plug it in and show it because it's not always going to be the case. So our points of inflection should be 1 over root 2 and 1 over root e, and negative 1 over root 2, 1 over root e. Everybody good with that now or no? All right, so the question you were just asking basically is this. Do we have to plug it in? Yes, because the second derivative can be 0 at a point that's not an inflection point. Or we might end up, we also need to be careful about making sure we check when it's undefined, because a lot of times people forget about checking when it's undefined. So just one basic example is x to the 4th. Your derivative would be 4x cubed, and your second derivative would be 12x squared, right? And never undefined, but equal to 0 when x is 0. And you make your sign chart, plug in a positive number and you get a positive, plug in a negative number and you get a positive. So we can see that it's concave up for the entire domain of this. Even though we had a place where the derivative, the second derivative was equal to 0, it doesn't guarantee us an inflection. Everybody see that? All right, so the second piece of this that I'm saying is we got to make sure that we check when it's undefined, because a lot of times people forget about that and they just look for when it's 0. So f prime is 1/3 x to the negative 2/3, and f double prime is negative 2/9 x to the negative 5/3. and this is negative 2 over 9x to the 5/3. And so this is never equal to 0, but it is undefined when x equals 0. And if we make the sign chart with a positive number, this comes out to be negative, and with a negative number, this comes out to be positive. And so we can see that there's a change in sign of the second derivative, and there's a point of inflection. Any questions on that?
So just to clarify, you do the sign chart for the first derivative for increasing and decreasing intervals, and you do the sign chart for the second derivative for concavity.
Yes, that is correct. All right, 1 second. I'm going to go to the next page. So read through this, see if it makes sense, and I'll be back in a second. I got to deal with something in my house for just a minute. Sorry about that, everybody. You guys all still there, alive and ready?
Sure.
Oh, good. All right. So we have what's called a second derivative test also. So the second derivative can also help. Oh, geez, I lost the ability to talk. The second derivative can also help us find if something has a maximum or a minimum at a critical value, but only at a critical value where the derivative is equal to 0. So not a place where the derivative is undefined. So sometimes it's helpful to take a second derivative. Like if you have a really difficult first derivative to make a sign chart with where it's hard to plug stuff in, but it's easy to take a second derivative, we'll use the second derivative test. So we should know that if the derivative is 0, that means we're going to have most likely a local max or a min. If our function happens to be concave up, what does that tell you about the second derivative? We know that it's positive, right? And if the second derivative is positive on an interval at which we have a place where f prime is equal to 0, then since it's concave up, it must be a local minimum. And the opposite is true also. If f prime is equal to 0 at a place where f double prime is less than 0, then it's got to be a maximum. Does that make sense to everybody?
That makes sense.
All right, good. So it only works when the derivative is 0, and if we can find a positive or negative value for the second derivative at that point. So let's go back to one we'd already dealt with before, x cubed minus 12x minus 5. Right, we found way back a long time ago, we found somewhere up here, we found that the critical values were x equals 2 and negative 2, right? Everybody see that? So we said f prime equals 0 and x equals positive or negative 2. And we had f prime was 3x squared minus 12. And we could say that f double prime is 6x. And so if we take 6x and evaluate it at 2, we get a positive number, 12, which tells us that at x equals 2, since the derivative was 0, and since this is a positive number, we should have a local min. And if we take 6x and evaluate it at negative 2, that gives us a negative number, which tells us that at x equals negative 2, we should have a maximum. And that's exactly what we found out using the sign chart. So everybody see that? Cool. All right, so we're going to make an attempt to graph a function using all of these different things that we've now learned. So we're going to try and graph x to the 4th minus 2x cubed. Anybody have a good idea on what we should do to start that off?
Find local maximum and minimum.
All right, local maxima and minima is one good thing. What's something we can do before we take a derivative? Anything we can do before we take a derivative?
On the domain?
Okay, domain, which we should see since this is a polynomial, the domain should be all real numbers. What else can we do without taking a derivative?
Factor out an x cubed.
Okay, we can factor out an x cubed. What that can help us do? If we set it equal to 0, that should tell us where we have
X-intercepts.
x-intercepts, right? So at x equals 0 and at x equals 2. So there's one at 0, and we'll say each 2 boxes is 1 unit, so there's another intercept at 2. So now we'll take our derivative. So if we take our derivative, 4x cubed minus 6x squared, we should see that that's never undefined, and it equals 0. We can factor out the 2x squared. And we can see that at x equals 0 and at x equals 3/2, we have potential local maxima or minima. How do we prove whether or not they are? What do we need to do?
Second derivative test or sign chart?
Second derivative test or a sign chart. Let's do the sign chart just for fun. 0 and 3/2. What's something less than 0? -1 or -1,000? If I plug in -1,000, 2x squared is positive and this is negative, so it's negative and it should be decreasing. Everybody agree with that? Okay, I'll take that as a yes again. What about if we plug in something between 0 and 3/2, like 1? That's positive, and this is also negative. So we still are decreasing. So do we have a local max or a min at 0?
No. No.
Nope. All right, and then plug in something more than 3/2, like 1,000, and we get a positive and a positive. So we get something that increases. So we do have a local min at x equals 3/2. We'll want to figure out what the value of f of 3/2 is. What's f of 3/2 equal to? 3/2 to the 4th power ought to be 81/16. And then minus, what is that, 27/8 times 2, so 27/4. So if we subtract those, what is that, 108, -27/16, looks like. So we can plug in the 0.3/2 and -27/16, something about like that. So we got that point. So that's at least one more point that we know we have a minimum at. And then we need to find some points of inflection or some intervals of concavity. So let's do that. We'll find a second derivative. So what's f double prime going to be? If f prime was 4x cubed minus 6x squared, f double prime should be 12x squared minus 12x. And never undefined, but equals 0. We'll factor out the 12x to get at x equals 0 and x equals 1. And if we make a sign chart with our second derivative, plug in something between 0 and 1, what do we get?
Negative.
Right, so like plug in a half, that's definitely negative. Plug in something negative, we get a negative times a negative, so that's positive. And plug in something greater than 1, like 1,000, we get a positive and a positive. So it looks like we have 2 points of inflection. One of them is at x equals 0, which we know we already have that point plotted, right? 0, 0. So we'll need to plot the point at 1. So what's f of 1 equal to? From the original function, that should just be 1 minus 2 or -1. So we'll plot that point of inflection. So we got 4 points, and we got a lot of information about increasing and decreasing and concavity. So we know that we're going to start on the left-hand side here. We know that from -infinity to 0, our function is decreasing as well as concave up. So it should look about like that. That's like the left-hand side of the parabola. And then at 0, 0, it should continue decreasing, but it should switch to being concave down. So from 0 to 3/2, it's decreasing, but it's concave down from 0 to 1. So it should flip and be concave down. Then it should continue decreasing to this local min, but now from 1 to infinity, it should be concave up. So once we flip here, it should be concave up again. So point of inflection, another point of inflection. And then at 3/2, it begins increasing and goes up. Oh, that's not very good. Nor was that. There we go. It goes up and increases and is concave. And that's what that graph should basically look like. My sketch isn't perfect just because I have trouble drawing on the laptop screen. But if we wanted to, we could take a look at it on Desmos. And it would look about the same as what we had, x to the 4th minus 2x cubed. Yes, John, you will have to use this in real life scenarios. Isn't this your real life right now? Taxi driving? I don't know. Wouldn't recommend that during a pandemic, but yeah, we're going to have some actual real life applications of derivatives and stuff. But you know, the biggest application is finding maxima and minima and using that in real world situations, which we will be doing either on Friday or starting next week. So, anybody have any questions about that last problem? That's the last one we're going to do. We'll do a couple more graphs tomorrow, but any questions on that or anything we've done today?
What is the quiz going to be on tomorrow again?
It'll have some of this increasing, decreasing concavity interval stuff, and that's really all you'll have on it, is figuring out where it's increasing and decreasing and where there's local maxes and local mins and points of inflection. I won't ask you to graph. And I'm going to post up an assignment that won't be due yet, but with some of you can practice. So if you have questions on them, you can let me know tonight and I'll be happy to answer them.